So I'm going to review how to make Lewis dot diagrams of covalently bonded molecules. I'm going to answer some questions regarding what kind of bonds are created between the two nonmetals, what kind of molecule in terms of polarity is it, and we're going to look at two types of geometry, electron domain geometry and also the molecular geometry as well the hybridization. So we're going to cover a lot of material here. And what's interesting is all this information, including bond angles, all results from Lewis dot diagrams. So starting with the Lewis dot diagrams, a lot of information can be had. So let's start with our first structure, and HI, high. Okay, always good to start with a high. So we have H and we have I, and H has one valence electron, and iodine has 7. You should know your valence electrons at this point, and that would take us to HI. Now you could draw it like this, H with an I. If you do it dashingly, you need to show the lone unbonded pairs. Okay, now, first and foremost, if I was to answer something about the hybridization, we'll just put HB, we would say none. No hybridization is needed here because these molecules, there's no central atom. We have a terminal atom, and we also have a molecule or an atom at the end that's also terminal. So there's no reason for having that. If you want to explain it even further, if you want to look at iodine, iodine has three P's. So here's P. Let's make that Py, Px, and then Pz is coming at you and into the board. Don't forget it has an S. So the valence shell has two valence electrons in the S, and they also have valence electrons in the P. If you notice, 1, 2, 3, 4, 5, 6, and I'll make this 7. So iodine has that sp2 and p5 ending of its valence shell, has 7 valence electrons. Hydrogen, this is just an S is spherical, has that dot there to be its valence electron. It's 1s1, it just has an S, so that represents the bonding. If you look at all the unhybridized orbitals, we can explain this linear shape. Two atoms bond together can only be linear. So it's linear for its geometry. We don't have an electron domain geometry. Electron domain geometry, that would be not applicable here because there's no hybridization. So the geometry of two atoms will always be linear. So we can explain this without hybridization, therefore there is none. The bond type is interesting. The bond type, we have two different nonmetals, two different electronegativities. So we would say that this is a polar covalent bond. The molecule type, well, because we're sharing electrons unequally, and I did not draw that well, I don't think. Because let me just draw that better. I mean, you don't have to, but here is the dot here, and here is the B here, and I'm thinking that iodine's a little more electronegative, but I have to actually look that up. But they're going to share unequally a little bit, okay, in terms of their regions curriculum. They're two different nonmetals, so it's polar covalent. In true, for those watching this that are not part of the regions curriculum, if you're within about 0.4 of the difference of the electronegativity, we consider it to be nonpolar. And that might be the case for HI, but in terms of the regions curriculum, two different nonmetals, two different electronegativities, so therefore the difference is not going to be 0. So we call it polar, at least in this curriculum. Okay, the molecule type, well, it has to be polar. If you only have one bond, and that bond is polar, then gosh darn it, the molecule is going to be polar covalent. There's nothing else for this bond. So there's unequal distribution of electrons. You have more electrons, let's say, toward the more electronegative atom. So therefore, there's the partial negative side, there's the partial positive. And the dipole moment would go from positive to negative, like that. Okay? And those are the only information I have. There's no hybridization. Electron domain geometry is not applicable. The geometry is linear where the atoms are, so that's the molecular geometry. All right, and the bond angle, if you want to do bond angle, of course, if it's linear, it's 180. Easy enough. Okay, moving down, I'm going to get rid of this little beautiful flower. Okay, now I got CH4, so I've got carbon in the middle, and I have my H's hanging around. Haha. And we have our carbon with 4 valence electrons, 1, 2, 3, and 4. And then we have hydrogen, each with a valence electron. And if you notice, just by sharing, okay, carbon feels like it has 8, and each hydrogen feels like it has 2. So we know we did this right. Remember, hydrogen wants to feel like helium, who has 2 electrons. Any case, I could also draw it this way if I wanted to be dashing. Dash represents a pair, and there I go. There's no lone pairs on the H, and I'm done. So the bond type, as we said before, 2 different nonmetals. We're going to call this a polar covalent bond because of the unequal sharing, because of the difference in electronegativity. That's in the Regents curriculum. If you're outside the Regents curriculum, carbon and hydrogen have an electronegativity difference of about 0.4. So we consider this in the entire world, except for New York State, to be a polar molecule. I mean, nonpolar molecule. In New York State, we call this polar because there's 2 different elements, 2 different electronegativities, but everything outside of New York State, according to the New York State Regents, this is a nonpolar bond. In any case, we're going to call it polar. We're going to stick by the Regents curriculum. The molecule type, well, you might say, well, it's got a polar bond, so it should be a polar molecule. Well, my friends, in chemistry, if we look at the dipole moments, okay, the more negative is the partial negatives are on the carbon side, and the partial positives, again, the reason for the partials is because these are not complete transfers. They're just being shared unequally. So the positive, okay, will point to the negative, point to the more electronegative atom. So I've got 4 dipole moments all pushing in together, the same arrows. Remember, arrows represent the dipole moment, which is really very similar to the difference in electronegativity. Since these are all the same atoms, all these arrows are the same size, and their direction is all pointing into each other, so they cancel out. So this is a nonpolar molecule. Even though it's got polar bonds, it's nonpolar molecule. As I said in class, because you're sharing electrons unequally in all directions, you're equal in your unequalness, so therefore there's no side that has a pole. Polar means you have a molecule, like I said, a difference of charge. Well, here you don't, because you're sharing electrons unequally, yes, but in all directions. Dipole moments cancel out, or as you say in some classes, because of the symmetry, you would say that the polar bonds would cancel themselves out, and there's no overall dipole moment. Now, before we get to the geometry and really understanding why this actually does cancel out, look at this. I want you to count for the hybridization. Okay, let's make that red and keep that consistent. For the hybridization, what I want you to do is look at the number of different places where electrons are around the central atom. So 1, 2, 3, 4. Now, if that's the case, that means an S and 3 P's came together to hybridize. Now, how do I know that? Well, S is 1, and there's 3 P's. Count how many checks there is. It's 4. That's 4 pairs of electrons, 4 different orbitals came together and mixed. So that's sp3. Now, the electron domain geometry, ED, represents just where those electrons are, and that's called a tetrahedral. That's the tetrahedral family. Okay, the molecular geometry, which I'll write down here, is also a tetrahedral. Now, why? Well, this is where the atoms are, and there are 4 atoms surrounding that central atom. Now, this is not a planar molecule. As I suggested before, it looks like it's planar. You have to understand, if I have the H and another H, the C is right in the middle, they're on the same plane. We have one going out and then one coming into the board. So this would be an H, C going away, and a C coming at you, okay, sort of on the side there. And that's the 3-dimensional nature. Oops, that's an H, and this is an H too. That's the 3-dimensional nature of that tetrahedral. It's like basically what it looks like. It's the top of a tripod, and then you have one on top. And those bond angles, I should say, the bond angle, I'll put that in blue to keep things the same. And I do have a little cold, thank you. Bond angle is 109.5 degrees. Okay, and we covered that. Bond angles, the different types of geometry, the hybridization. Okay, and again, you have to explain this with hybridization, because if I try to do carbon unhybridized, as I'll do here, here's one p, here's another p. Remember, there's 3 orbitals, so here's the 3rd orbital, and then here's the s. It has 4 valence electrons. So let's make this 1, 2, 3, 4. Okay, well, if an H comes in bonds, which would be a spherical, you would have a 90-degree bond angle here. So this would also be 90-degree bond angle, no matter what you do here. But we know from experience that it's 109.5, so it has to hybridize. We can't treat these as unhybridized orbitals. It just doesn't work. Central atom, if it's bonding to more than one thing, unlike number 1, has to be hybridized. Okay, I too like to do this worksheet. Haha. So we got high and we got I2. So iodine bonding with iodine. One iodine has 7 valence electrons, and another iodine has 7. I'm color coding these just to show you the valence electrons, but once they are part of the bond, it doesn't matter whose is whose. And of course, by sharing, this iodine feels like it has 7, and this iodine, by sharing, feels like it has 7. Of course, you could rewrite this as I, if you want to be dashing, into I. Make sure if you're dashing that you you draw the lone pairs, unless it won't be right the otherwise. Okay, the bond type. Well, because they're the same atom, they have the same electronegativity, they're going to be pulling on these electrons equally. They'll be sharing equally right down the middle. So this is going to be a nonpolar covalent bond. Nobody feels the electrons on either side of the bond. Equal distribution. Okay, so nonpolar covalent. The molecule type also has to be nonpolar. And you say, well, why? Well, because there's no dipole moment, because there's no polarity, there's no polar bonds. If you don't have any polar bonds, which is the source of your unequal distribution of electrons that creates the polar nature, you cannot be a polar molecule. If you have a polar bond, it's not automatic that you're a polar molecule, because in the case of, let's say, methane, that polar nature or that symmetrical nature will cause the polar bonds to cancel out, or their dipole moments, however you learned it. Now let's go back to the hybridization. Well, there's only 2 atoms, so obviously the geometry is linear. But because there's only 2 atoms, we can explain this without hybridizing. So we say there's no hybridizing here. And you say, well, how can I explain without hybridizing? Well, same idea here. Here's a P of 1 iodine. Here's an unhybridized P of a oops, bad Grotsky. Here's a unhybridized P, and this is the P coming at you and going back. Now, if you didn't follow what I'm doing here, this is P Y, so is this. Oops, and this is P X and P Z. If you're trying to understand here, P's have 3 boxes when you do orbital notation. And this could be, if you want to do X, Y, Z if you want. There's 3 different orbitals, and this is one orbital here. Here's another orbital, here's another orbital. Also, if you're unhybridized, you have an S. All right, and that S holds 2 electrons. And let's just do that in a different color, because I can. So we have 2 electrons in the S. We have 1 here, 1 here. Notice that fills that P. We'll have 1 here and 1 here that fills that PZ. Okay, so the PZ is filled. The S is filled if I draw that over here. The X is going to have 1 only, so I'll just put that one there. And the Y, this is my Y is filled. My Z is filled, and my X has 1. So this is 1 iodine atom. Okay, and I'm going to draw the same thing over here. Just do the opposite. So here's another, from another iodine atom that's not hybridized. Remember, hybridization is just what? Is just a theory that helps describe what's happening. We don't know for sure if this is exactly happening, but it explains things nicely. So I'm trying to draw these orbitals not very well today. So this iodine has 2 in the S, 1 in the PY, 2 in the PY, 2 in the PZ, and another one in this PX here. And that's the second one, and that's the bond. It's linear because it's 2. Notice everything is filled. Don't fall in love with the fact that you could bond over here now. This is a PX, and PX holds 2 electrons. All these P's are filled. That's why you can't have an essential atom like carbon bond on either side with unhybridized P's. Once you, what? Bond to one of the P's, you can't bond to the outside. So this is not hybridized because it's not a central atom bonding on both sides. It's just bonding terminally with its unhybridized P's. Okay? So that's how you gotta start thinking about this. So there's no hybridization. Electron domain geometry is not applicable here because it's not hybridized. The bond angles is going to be 180 for anything that's just 2 atoms, has to be linear. Okay, and there is no hybridization, as I said. Okay, NH3, here we go. NH3, we have the N has 5 valence electrons. Now, so why did I write it like that? Why did I write my dots like that? I tend to do that because an old-fashioned way is to write the S electrons here and the P electrons here. Because if you know, N has 5 valence electrons, and it's famous for having 3 lone pairs. That's why I write it that way. Then we have the H's. Each H has an electron. And that's our Lewis structure. Easy to do. Nitrogen by sharing feels like it has 8. Each hydrogen feels like it has 2. Okay, because these are 2 different nonmetals, okay, the bond type is going to be a polar bond. Electrons are going to be shared unequally. The nitrogen is much more electronegative than the hydrogen. This is a 2.2. Nitrogen is about 3.0. So the partial negatives will be on the nitrogen. The partial positives will be on the hydrogen. So this is a polar covalent. The molecule type, well, it does have a polar bond, so it's got a chance to be polar. However, because of its shape, and that's why we have to think three-dimensionally, that's why we have to think in terms of VSEPR theory and hybridization. We have to understand its shape, okay? Because if you thought that this was trigonal planar, if you thought that N bonded with H like this, that's very symmetrical and polar, and the dipole moments would cancel out, and this would be nonpolar. So we have to understand the shape. It does not do this. And what helps us understand this is hybridization. So the hybridization here, what is it? Well, it's definitely hybridized. The central atom is going to have hybridization. The only way to explain this. Now, how do we figure it out? Well, same thing we did before. Count the pairs of electrons in each direction. 1, 2, 3, 4. That means an S and 3 P's came together. That's the hybridization. Now, the electron domain geometry is the geometry of where the electrons are. In sp3, it's always going to be tetrahedral. And I'll just put tetra, and that's tetrahedral. The molecular geometry right here, with 1 lone pair in the sp3 family, if you think with me for a second, here's the lone pair on top. Then we have what? 1 coming out, 1 coming at you, and 1 pointing down, top of a 3-sided pyramid. Yeah, it's the top of a 3-sided pyramid when you just consider where the atoms are. Molecular geometry is where the atoms are. So trigonal, same thing as triangle. And we put pyramid or pyramidal is the shape. And that's for 1 lone pair in the sp3 family. Okay, now this is not a symmetrical shape. Okay, if you want to think with me, if you drew the N with two lone pairs in the H, and you drew it like this, even though it's not planar, you could probably get away with thinking, hey, okay, I got a positive going to a negative, a positive going to a negative. And if you look at your arrows or your dipole moments, these two would cancel and this one wouldn't. This is a polar molecule. And the overall arrow, okay, would be from those really in the middle of these hydrogens up into the nitrogen if you think three-dimensionally. So it'd be through the nitrogen up into, pointing directly at the lone pair. And there's an overall dipole moment. If something is polar, I better see that. Notice we've had nothing polar so far except for number 1, and there's the overall flow of charge. Okay? So this has polar bonds, and because the shape is asymmetrical, which means that the polar bonds don't cancel or the dipole moments don't cancel, this is going to be, okay, a polar molecule. And you're going to have the negative end where the N is, and the positive ends, and I should say partial again, where the H is. So this end here is the partial positives, and here is the partial negatives. You have to think three-dimensionally. Okay, N2. Let's get some space for myself for N2. All right, so N2, we have nitrogen, and I'll keep doing that. And then we have another nitrogen. We'll keep this one blue. And same idea. And the first thing you do Lewis dot diagrams, put all the valence electrons out, and then just make one bond, as I did here. Now, if you count with me, this nitrogen feels like it has 2, 4, 6. This nitrogen feels like it has 6. So that's not going to work. That would not be stable for a second row element. So what I'm going to do is move one of these electrons over, and I'm going to move another one. Before I do that, let's make sure this is nice and neat. I'm going to erase this, maybe move this over, blue here, and then I'm going to move this one over here. And if you see something, now it's a double bond. Now, if you share the electrons from this nitrogen, you see that this nitrogen feels like it has 2, 4, 6, 7. This nitrogen 2, 4, 6, 7. Not going to work. We're going to need a triple bond. So I'll move this one over, and I'm going to move this one over. Easier for me to do, I know. Okay, and if you notice, everyone's stable because everyone feels like it has 8. Nitrogen, if you want to draw it, triple bonds. Every dash is a pair of electrons. Don't forget, if you're going to be dashing, you put in the lone pairs. Okay, now of course, you should see some things here. The bond type is going to be nonpolar. As we talked about before, if you're bonding to the same atom, you're going to share electrons equally. There's no difference in electronegativity. Nobody feels more electrons. There's no unequal distribution of electrons. They're being pulled evenly right down the middle. So it's nonpolar covalent. Now I'm writing covalent here, but you hear polar or nonpolar. That's pretty exclusive for covalent bonding, not ionic. Okay, moving forward. SP, hybridization. And you can guess. Tell me, what do you think it is? If you said none, you're correct. 2 atoms don't need hybridization. Okay, 2 atoms do not need hybridization. You can explain it without it. Now, some people think that nitrogen is hybridized for these lone pairs to stick out like this. And some people say, well, that when they bond, they become hybridized. But I'm going to say, and stick to my guns here with my class, and say that this atom does not need hybridization to explain how N bonds with N. And you may say, well, how can I do that? Well, real quickly, if I draw my P's, all right, PY, PX, and PX is the same one, PZ. Okay, and each one gets 1. Okay. All right, I draw another one. I'm going to leave the 2 and the S by itself. You know the S is there. Here's another one. This is going to overlap, poor drawing. And this is my Z. Okay, I'm going to make these blue because I'm feeling blue. This one's going to overlap. That's the first bond. This one goes here. And then this one will go, let's say, here. You may say, Mr. Growski, how can the other 2 bonds occur? Well, we're going to call this a sigma bond, which is called direct overlap. And you're going to learn in a day or two that this p orbital will actually overlap this p orbital. There is some space. It's not perfect. We call that a pi bond. So notice this is one orbital that has one, this is one orbital that has one, and that electron can actually jump top and bottom and be shared between those two. And that's the second bond. And if you notice, there's one in the front and one in the back that can make the triple bond. So that's how I can explain the bonding without hybridization. Okay, now if you didn't quite get that, we're going to do more of those. But if you think they're something very simple, nitrogen is not a central atom, it's only bonding terminally on one side. We don't need hybridization. So electron domain geometry is none or non-applicable. The geometry has to be linear of two atoms. The molecule type is of course nonpolar because I don't have a polar bond. I have no place where there's an unequal distribution. No polar bonds, the molecule can't be polar. Okay, last one, silicon dioxide. Silicon has 4 valence electrons, like carbon. It's in the same It's in the same group. Oxygen has a 6, so I start with one bond, and I put in 5 dots. Okay, and that's not going to work, is it? This oxygen 1, 2, 3, 4, 5, 6 feels like it has 7. This one feels like it has 7, and this silicon feels like it has 2, 4, 6. No good. So all you can do is add more bonds. So I'm going to move that one here. I'm going to move this one, maybe. I'm going to move, hold on, this one, which is black, here. And you notice this oxygen feels like it's stable, but this silicon feels like it has, if you just count with me, 2, 4, 6, 7. If you don't know where I'm getting that, it's right here. So this one feels like it has 7, not good enough. So I do the same thing I do on the other side. Get rid of one. Okay, and then pair up the other one and make a double bond on both sides. And what you can see here, party people, is that this one is here. Silicon doesn't have any electrons above or below. And so silicon, if you draw it another way, is dashing. If you draw it like this, drawing the lone pairs, there's 2 of them. And this is the shape of the molecule. You can see it has to be linear because there's no electrons above or below to push it down. So the bond type between the Si and the O, because they're 2 different nonmetals, has to be polar covalent. Now the molecule type depends if you're understanding the 3 dimensions. So let's go to the hybridization. What do you think the hybridization is? Well, it looks like it has to be linear because that Si has no electrons pushing it down, so it has to be Sp. And you say to me, Mr. Grotsky, how do I figure that out? Well, count the pairs of electrons in one direction. 1, 2. I know there's 2 pairs here, but they're all in the same plane. So an S and a P had to come together, and Sp is always going to be, as we've learned, linear. So electron domain geometry is linear. The bond angles are going to be 180. The molecule type, if you haven't already guessed, because it's linear, this dipole moment, which this would be the positive end, this would be the negative and the more electronegative. So we go what? Positives flow to negatives. We got 2 arrows in opposite directions. They would cancel. Or you would say it's symmetrical. Therefore, this is a molecule that has polar bonds, but because of its symmetry that we can understand as 3-dimension, it's a nonpolar molecule. I forgot to do this guy right here. This bond angle for an sp3 tetrahedral is about 109.5. However, because of the lone pairs will push this lower to about 107. But if you don't have that, it's okay. All right? That really reviews that ditto. And these are the things I need you to pick up. Okay? Thanks.